morning everyone. So this is my fifth lecture based on Z transform and properties of ROC, and the subject intended to this lecture is basic signals and systems, and the code is BEE 303, and this course belongs to EN students. So what we will do here, we will see the Z transform basics, the Z transform properties and its ROC, how it is different from Laplace transform, and how it can be more effective as compared to Laplace transform. What are the differences between Z transform and Laplace transform? So what we do here, the motivation behind the Z transform, another important mathematical tool which we are studying in the signals and system is known as Z transform. The Z transform can be viewed as a generalization of the Fourier transform, or in Z transform we can have discrete type of sequences. So if you compare the Fourier transform with Z transform, Fourier with Z, so Fourier transform has two parts, that is CTFT, that is continuous time Fourier transform, and the discrete time Fourier transform, and the Z transform belong to discrete time Fourier transform, equivalent of discrete time Fourier transform, or you can say for the discrete time sequences Xn, we can find out discrete time Fourier transform, and also we can find out Z transform. So if you compare the formula of Fourier transform with Z transform, so Fourier transform formula is x of omega or x of j omega, x of j omega can be written as minus infinity to infinity x of t e to the power minus j omega t dt, like this. What we have, the Z transform, due to its more general nature, we can have the Z transform has a number of advantages over the Fourier transform. First, the Z transform representation exists for some signals that do not have Fourier transform representation. So we can handle a larger number of class of signals with the help of Z transform. Second, since the Z transform is a more general tool, it can provide additional insight beyond those facilitated by the Fourier transform. So I am discussing about Z transform formula, that is x of Z is summation over n equivalent to minus infinity to infinity xn z to the power minus n, and the discrete time Fourier transform is represented as x of e to the power j omega summation over n equivalent to minus infinity to infinity. This is for Z transform, and the counterpart for Z Fourier transform is x of n e to the power minus j omega n. So if you compare both the equation number 1 and equation number 2, you will find z is equivalent to e to the power j omega. For having x of e to the power j omega is equivalent to x of z. So if you put z is equivalent to e to the power j omega, then the Z transform will be converted into Fourier transform. You can see from the expression itself. So next, what is bilateral Z transform? So when we talk about bilateral Z transform, it means the Z transform for the range from minus infinity to infinity. So the bilateral Z transform of the sequence x denoted by Z of x or capital X is defined as x of Z, which I have written earlier, that is from n equivalent to minus infinity to infinity xn z to the power minus n. The inverse Z transform is then given by Z inverse of xn, or xn can be written as 1 upon 2 pi j closed integration of x of z, z to the power n minus 1 dz. We don't use this formula for calculating the inverse Z transform. Basically, we use partial fraction method for Z transform. There are three methods: partial fraction, second is long division for inverse transform calculation, and third is residue method. We can use also residue method for calculating the inverse Z transform. Basically, we use these two methods more frequently for that is partial fraction method or long division method. Residue method you can also use for calculating the inverse Z transform. So here x and capital X as a Z transform pair and denote this relationship as x of n, the Z transform of which is x of Z. In practice, we do not usually compute the inverse Z transform by directly using the formula from the above. Instead, we resort to other means which to be discussed later on, which is basically partial fraction method or long division method. So the two different versions of Z transform are commonly used. First one is the bilateral, which is two-sided Z transform, that is from minus infinity to infinity. So if we write bilateral Z transform, it will be xz is equivalent to n equivalent to minus infinity to infinity xn z to the power minus n, because the range is from minus infinity to infinity. If we talk about unilateral Z transform, then n equivalent to 0 to infinity xn z to the power minus n. This is for right-sided sequence. For left-sided sequence, xz is equivalent to n equivalent to minus infinity to minus 1 xn z to the power minus n. So here we use the sequences from n equivalent to minus infinity to minus 1 and then 0 to infinity. So this is for right-sided sequence and this is for left-sided sequence. So the unilateral Z transform is most frequently used to solve systems of linear difference equations with non-zero initial condition. We can also use initial conditions. By putting the initial conditions, we can find out the solution of the difference equation. As it turns out, the only difference between the definitions of the bilateral and unilateral Z transform is the lower limit of the summation. So we have already seen the lower limit of the summation n from minus infinity to infinity is for bilateral, and for unilateral 0 to infinity or from minus infinity to minus 1. In the bilateral case, the lower limit is minus infinity, whereas the unilateral case, the lower limit is 0. For the most part, we will focus our attention primarily on the bilateral Z transform. We will, however, briefly introduce the unilateral Z transform as a tool for solving difference equations. So what is the relationship between Z transform and DTFT? So we have already discussed, but we can see in the detailed form. Since the DTFT of a discrete time sequence xn is given by x of omega or x of e to the power j omega, you can also write as x of e to the power j omega, this term is equivalent to n equivalent to minus infinity to infinity xn e to the power minus j omega n. For the existence of the DTFT, the sequence xn must be absolutely summable. Also, the summation in the above equation should converge. Thus, the Z transform of the sequence xn is given by x of z or Z transform of xn, that is from minus infinity to infinity xn z to the power minus n, where x of n or xn is the discrete, in the normal brackets you can write or in the square brackets you can write, are the discrete sequence. So, suppose there is a value for xn given in the question, that is from minus 1, 0, 1, 2, 3, and you have to find the value of x of z. So here from this is 0, value at 0, n equivalent to 0 is 0, n equivalent to minus 1, it is minus 1, n equivalent to 1. So this can be, it is x of 0 is 0, x of minus 1 is minus 1, x of 1 is 1. Similarly, x of 2 is 2, x of 3 is 3. By putting the values in the expression, x of z is equivalent to summation over minus 1, n equivalent to minus 1, 2, 3, x of n, z to the power minus n. We can get the values like x of minus 1, z to the power 1 plus x of 0 plus x of 1, z to the power minus 1 plus x of 2, z to the power minus 2 plus similarly values for plus x of 2, z to the power minus 2. So what we can do, we can put all the values, that x of minus 1 value, that is basically like, so if you put the value here, so when you put the value, x of minus 1 is minus 1, z to the power 1 plus 0 plus 1 into z to the power minus 1 plus 2 into z to the power minus 2 plus 3 into z to the power minus 3. We have the value minus of z plus z inverse plus 2 z to the power minus 2 plus 3 z to the power minus 3. This is the value for the sequence and the z transform for the sequence x of n, which is minus 1, 0, 1, 2, 3. So for the existence of the DTFT sequence, xn must be absolutely summable, where z is a complex variable here, and it is given by z is equivalent to r e to the power j omega, where r is the radius of the circle. If the radius of the circle is unity, then this z becomes e to the power j omega, and now the DTFT becomes the same as z transform. So what is the relation? X of z is equivalent to x r e to the power j omega. When you put in place of z to the power minus n, r e to the power j omega, you will get x n r to the power minus n in the same bracket, and the separate thing is e to the power minus j omega n. So if you compare, then this xz is DTFT of x n r to the power minus n e to the power minus j omega n, and if you put the value r equivalent to 1, then xz is equivalent to x n e to the power minus j omega n, and in that case DTFT becomes equivalent to Z transform for the sequence x of n. So if r is equivalent to 1, then the discrete Fourier transform DTFT is same as the Z transform. In other words, the DTFT is nothing but the Z transform evaluated along the unit circle centered at the origin of the Z plane. So there are some numerical problems based on Z transform, which are the basic problems. So first we find the Z transform xz of the sequence where a is a real constant. So if we have the sequence xn is equivalent to a to the power n un, which is basically exponentially growing sequence with the it depends on the value of the a. So from the definition of the Z transform, if we take xz is equivalent to summation over n equivalent to minus infinity to infinity a to the power n un z to the power minus n, and we know un is equivalent to 1 for n equivalent to 0, n greater than equivalent to 0, and 0 for n less than 0. So we can have xz for this from n equivalent to 0 to infinity a to the power n z to the power minus n. You can see, and when you solve it, n equivalent to 0 to infinity a z inverse to the power n, and this is 1 plus a z inverse plus a z inverse plus so on, like this. In order to simplify the summation converges for a z inverse less than 1, or we can have mod z greater than a. So when you see this relationship, this is a geometric progression, and you have a, that is a upon 1 minus r is the geometric progression for this series. So this is 1 upon 1 minus a z inverse, or we can have z upon z minus a. So if you see the ROC is basically mod z greater than a for this particular right sided sequence. So here we can have this thing, that is a to the power n un, the Z transform is 1 upon 1 minus a z inverse, and the ROC in mod z greater than a. What is ROC in the Z transform? This is real of z, this is imaginary of z. There is a unity circle which is having pole 1 and a circle which is having pole a. So here we are representing mod z greater than a, means the exterior of this circle, if a is greater than 1 in that case. Similarly, if a is less than 1, so this is the circle of 1 and this is the circle for a, this is real of z, this is imaginary of z, and for a, z greater than a, for z greater than a, this is the scenario for ROC. So here a is less than 1. These are two cases. This is case 1 and this is case 2. Example 2. Find the Z transform X of the sequence where A is given as a real constant. So xn is equivalent to minus a to the power n u of minus n minus 1. So firstly you have to see u of minus n minus 1. What is its range? So it is 1 when minus n minus 1 greater than equivalent to 0, or n less than equivalent to minus 1, and 0 when minus n minus 1 less than 0, or n greater than minus 1. So if you see here, then you will get to know that exact the limit of the summation is from minus infinity, n equivalent to minus infinity to minus 1, because after minus 1 it has a value 0, and before -1 it has a value 1, minus a to the power n and z to the power minus n. We can write like this, and when you solve it, because both the limits are negative, so we can make it positive, n equivalent to 1 to infinity, and in that case the value of the n is replaced by minus n. So minus a to the power minus n, z to the power n, like this, or n equivalent to 1 to infinity. When you replacing the limits in the summation, you have to replace the value sign of n in the expression also. So a inverse z to the power n, and when you solve this, you will get this particular expression, that is it's like x of z, you have x of z, that is summation over n equivalent to 1 to infinity a inverse z to the power n, and when you solve it, a inverse z plus a inverse z ka square plus a inverse z ka cube plus so on, and when you have this, the relation is 1 minus r, a upon 1 minus r, so this is GP. So we have a inverse z upon 1 minus a inverse z, and this is z by a upon 1 minus z by a, or it will be z upon minus z upon z minus a. So ROC in this case, because it has a minus sign already, so we have to check with a negative sign also, sorry, this one, and this becomes no plus. So the ROC is, because it's a left sided sequence, mod z less than a. So when you draw the ROC, it's the region, suppose this is 1 and a is greater than 1, and this region, this is real of z and this is imaginary of z. The inside of the circle with a radius a is the ROC here. So here also we can have two cases, when a is greater than 1 and when a is less than 1. So what is region of convergence for the Z transform? Region of convergence consists of concentric circles centered at the origin in the complex plane. If the sequence xn has a rational Z transform, then the ROC does not contain any pole and the ROC is bounded by poles or extends to infinity. If the sequence xn is finite duration, then the ROC is the entire complex plane except possibly the origin and or infinity. So we have to see what is the region of convergence according to the expression. If it is a right sided expression purely, then the ROC is mod z greater than value. If it is left, mod z less than value, and if it is bilateral, then it between mod z greater than a or less than, then there will be two concentric circles, and inside the region of that concentric circle is the region of the convergence. So region of convergence for the Z transform, if the sequence xn is right sided and circle z equivalent to r0 is in the ROC, then all finite values of z for which mod z greater than r0 will also be in the ROC. That is, the ROC contains all points outside the circle. So as compared to the Laplace transform, where we have seen a strip which is parallel to the j omega axis, and according to that we have to write the ROCs. Here we have to write the ROCs as like the interior of the circle or as the exterior of the circle. So if the ROC is the exterior of the circle or outside the circle, then that must be a right sided sequence, and if it is in the interior of the circle, then it must be of the left sided sequence. If the sequence xn is left sided and the circle z is equivalent to r0 is in the ROC, then all possible values of z for which mod z greater than 0 less than r0 will also be in the ROC. Thus, the ROC contains all points inside the circle except possibly the origin. If the sequence xn is two-sided, then the circle z is equivalent to r0 is in the ROC, and the ROC will consist of a ring that includes the circle. That is, the ROC is an annulus centered at the origin containing the circle. So thus we have three different cases. First one is mod z suppose greater than a, then second one is mod z less than a. This is for right sided, this is for left sided, and for mod z greater than a and less than b, this is for bilateral. So now if the Z transform Xz or Xn is rational and Xn is right sided, then the ROC is a region outside the outermost pole. If Xn is causal, then the ROC also includes infinity. If the Z transform Xz or Xn is rational and Xn is left sided, then the ROC is the region inside the innermost non-zero pole. And if Xn is anti-causal, then the ROC also includes the origin. So there are some properties of the Z transform. We just go through these properties in a hurry. So linearity is the property which we have already discussed in Laplace transform. All these properties, there are some properties which are different than Laplace transform because it's a discrete time sequence. So in linearity, a1 x1 and a2 x2n is the time domain version, and when you put this time domain, we take the transform of this time domain sequence, you will have a1 x1z, a2 x2z in the frequency domain or in the z domain. Similarly, time shifting or translational, that is x n minus n naught, the z transform of which is z to the power minus n naught xz. Complex modulation, a to the power n xn, and the z transform of x of z by a. Similarly, conjugation, x conjugate n, x conjugate z conjugate. Time reversal, x of minus n, and the z transform of which is x of 1 by z. Again, upscaling, m times of xn, that is x of z to the power m. Downscaling, we have 1 upon m summation over k equivalent to 0 to m minus 1, x of e to the power minus j 2 pi k divided by mz 1 upon m. Then convolution, x1 and convolution x2n, which is very important property, this one. Then x1z, convolution in time domain and multiplication in frequency domain. Again, it is similar to Laplace transform. Then z transform differentiation property, n multiplied with n xn, and it comes out to be in z transform minus z d of dz x of z. Then difference property of the z transform, x of n minus x of n minus 1, and the value is 1 minus z inverse of xz. This expression which we have already find with translational, which is time shifting, and a simple z transform of xn. Then accumulation property, summation over k equivalent to minus infinity to n xk, and the z transform is 1 upon 1 minus z inverse xz. So these are some properties, and we can have the property based questions on z transform also. We can solve with the help of these properties. So there is two more properties which are very important, initial and final value theorem, which we have already discussed in the Laplace transform. So initial value theorem gives the value of xn at t n equivalent to 0, and n equivalent to infinity, we will have the final value, that is limit n tends to infinity xn. So in the initial value, we have x of 0, limit z tends to infinity xz, and the final value n tends to infinity, limit z tends to 1, 1 minus z inverse xz, or we can write z minus 1 of xz. So these are some references of the z transform. You can use these books for having the glimpse of this z transform basics and the properties based on z transform. You can have numerous of examples based on z transform. You can use Oppenheim book or T. Rawat or BP Lathi for having a glimpse of signal processing and linear systems. Then you can solve multiple difference equation questions based on z transform with the help of difference property, which is very important, and we can calculate the transfer function, impulse response, or we can say system function or impulse response, which we have already discussed in the Laplace transform. The similar way we can use that particular thing in the z transform. So you can have this particular books for your reference to have the majority of the glimpse of the z transform, so that you have a good practice of the z transform basic. Thank you so much. We will meet in the next lecture.